Just as we've seen that the tangent line slope comes from taking a secant line slope and making the points become closer and closer together by using a limit, we can get the instantaneous rate of change from the average rate of change. If we look at an interval x to x plus a little bit, then we get the difference quotient as our rate of change in y or change in x, f of b minus f of a. B minus a would be h if you simplified it. And then you shrink this little bit, this little change here. You let that go to 0. And that gives you the instantaneous rate of change, or IROC, at one single point. We can and will often just call this rate of change. That will just mean instantaneous rate of change. Okay, so just note here that this is the derivative. Instantaneous rate of change is just f prime of x. This is the derivative of the function. Now, something to note in particular is that if your function y, or f of x, is something that models distance and x is measuring time, then the rate of change, or the instantaneous rate of change, or the derivative, is just what we would call velocity. Velocity at one point in time. No, actually, if you have ever gotten pulled over by a cop on the side of the road, the reason that they can calculate your speed or your instantaneous velocity is by using a radar gun. And what that radar gun does is it actually calculates your average velocity, but for a very, very, very tiny time interval. And that can give them an idea, a pretty close measure of what your instantaneous velocity is. Sometimes it can be hard to distinguish whether we want to use average rate of change or instantaneous rate of change. Although normally a problem will say, like, find the average rate of change of something versus just the rate of change, which can be a good indicator of which that you're looking for. But here's a sort of mind map of the ideas that we've been talking about and how they're connected. If we want to find the secant line to a curve between 2 points, and we're looking for the slope of that secant line, this is given to us by change in y over change in x, or f of b minus f of a over b minus a, where we have 2 points, a comma f of a and b comma f of b. We also just saw that this can be interpreted in a context as the average rate of change over the interval from a to b. So over here on this side, this is all average rate of change stuff, or secant line slope. On the other side, we have instantaneous rate of change stuff, or tangent slope, depending on the context that we're working in. If we're looking to find the slope of a tangent line that goes through one point on a curve, then this can be given to us, as we saw, the long way with the limit definition of a secant line slope between 2 points, and then shrinking the points closer together. This in words is a derivative at x equals c, and in symbols it's f prime of c. We can also interpret this as the instantaneous rate of change, or just plain rate of change at x equals c. So again, I know we've been talking about several different ideas, but really they're all very much related. I hope that this mind map here can help you organize the ideas a little bit more. Let's look at an example of finding instantaneous velocity. Here's a little bit of physics for you. The general position function for a free-falling object, if you neglect air resistance, which would make this more complicated, is given by this formula. H equals negative 16 t squared plus v sub 0 times t plus h sub 0. So what these symbols mean, I mean, t is the variable, so your formula is going to have a t squared in it and a t here. But the v subscript 0 here, this is actually the initial velocity, or at time equals 0, it's the velocity of the object. This h sub 0 is the initial height, or the initial position. If you plug a 0 in for t, then both of these terms go away and you just get this constant term. So that means that at t equals 0, your initial height, or the starting height, has to be this number here. The negative 16 has to do with a constant acceleration, which is due to gravity. So in this example, we have a situation where at time t equals 0, the beginning, a ball is tossed upward off the top of a 64-foot building. The ball is tossed upward with an initial velocity of 48 feet per second. So that means that the height function at any time t is given by h equals negative 16t squared, then plus our initial velocity of positive 48 because the ball is tossed upward, 48t, and then the 64 is the initial height because that's the height of the building, so we have plus 64. In part A, we want to know when does the ball hit the ground, and then in part B, we want to know what is the ball's velocity at the point in time when it hits the ground. So if we draw a picture of this situation, then we have a building here, and here is where the ball is tossed upward off of, and then eventually, of course, based on our experience of the world, we know that this will turn around and come back down and fall to the ground. The initial height being 64 means that this is the height of the building, and that at this point here, when t equals 0, the height is 64. We're also told that at this point when the ball is tossed upward, the initial velocity is 48 feet per second. Right, this has a positive velocity at this point in time because the height is increasing or going up, but right around here, when the ball starts to turn around, its velocity should be negative that whole time. So on our picture, the place where the ball hits the ground, again, is right here. So we're looking for this time, and the only thing we know about this is that the height here is equal to 0. So that means we're going to find in our original equation here, the one that gives us height at any time, we want to find the time when the height on the left-hand side, when we have a 0 out here. Okay, so we're going to set our height equation equal to 0. So negative 16t squared plus 48t plus 64 is equal to 0. Remember that to solve a quadratic equation, when we have a t squared and a t to the first in the same equation, what we have to do is get 0 on one side of the equal sign, which we already have, and then we have to either factor or use the quadratic formula. I see that there's a negative 16 in front of the t squared. It would be really nice if we could actually take out a negative 16 as a GCF from each term. And I think that each one of these numbers is actually divisible by negative 16. So if we factor that out, we'll get positive t squared, then 48 divided by negative 16 gives us negative 3t, and then 64 divided by negative 16 will give us minus 4. Now we can leave this negative 16 out in the front and hopefully try to factor this into two linear pieces by looking for two numbers that will multiply to negative 4 and add up to negative 3. And I think we have two such numbers, negative 4 and positive 1. Okay, so setting each of the three factors here equal to 0, negative 16 is never 0, so that won't give us any solutions. The t minus 4 is equal to 0 when t is equal to 4, and t plus 1 is equal to 0 when t is equal to negative 1. We can actually ignore this t equals negative 1 because we're starting at t equals 0. We don't have any reason to use a negative time in this situation. So our only values here will be t equals 4. So t equals 4 seconds. So instead of a question mark here, we can actually change that and note now that it takes 4 seconds from when the ball is initially tossed for it to hit the ground. In part B, we want to know what is the velocity at that point in time. So this isn't the velocity over some range of time or over an interval, it's the velocity at one single point in time. This is an instantaneous rate of change. This is instantaneous velocity. So we want to find the derivative, and then we will plug in 4. Pause this video and take the derivative of the height function. You should get that h prime is equal to negative 32t plus 48. Now we want to find the velocity at the point in time when t equals 4. So we're going to substitute in a 4 into the velocity equation, or into h prime. That will give us negative 32 times 4 plus 48. And if we simplify that, we will get negative 80. Now, this is a rate of change. It's a velocity. So we want to make sure that we include some units here. Remember that units for rate of change are the output measure over the input measure. The output of this function is h. That is measured in feet. The input variable in this function is t, and that is measured in seconds. So the units for our velocity will be feet per second.